All right, here we are to talk about an old AP free response problem. This one's from 1982, so that's, really old. How old? Well, not as old as me, but I was 10, okay? So it's old. So anyway, let's take a quick look at it. I would say just first off that this problem is considerably less intense than AP free response problems you'll see nowadays. It only has 3 parts, and frankly, some problems are harder and some are easier. This one's kind of on the easier side overall. Let's take a look at it. So what they tell you is that we have, they drop us down some coordinate axes. So we have an x-axis and a y-axis, and they say, hey, we've got 3 point charges. Okay, we've got right here we've got a charge that is a positive q, and then symmetrically on the other side we have another charge that's plus q, and then right on the axis there, okay, we have right at the origin of the coordinate system we have a negative q charge. Okay, and they go ahead and they give you a couple values. They tell you, hey, we're going to say that this distance here is a, and this distance here is a. So we're symmetrically a distance a away from the axis, and yeah, that's really it. That's the setup. And so the first thing they ask is, can you find points on the x-axis where the electric potential is going to be 0? So the first thing that comes to my mind is that I know we define potential to be 0 at an infinite distance away from the charges. So I know that if I went all the way out to positive infinity and all the way out to negative infinity, x equals plus or minus infinity, the v value would be 0 there. Okay? And that's fair to say that. The thing is that the only spots where the potential would be 0? So I started thinking about it. I know that the formula for electric potential for a point charge is just kq over r, okay? Where this is the charge q making the field, and this is how far away from that charge I am. If I have a bunch of charges, I just add up all the potentials. All right? So in this case, and we're looking for a spot on the axis. So I might just invent a position here and call that location, say that that is at a position x, variable x out from the origin. And say if I wanted to find the v value there, I would just add up the v's from the 3 charges. And you say, now, I know that if I was really up close to this negative guy, right, my potential value is going to be lower than 0, or it'll be really low. And as I go farther out, then you're like, okay, when the potential eventually when it gets to infinity, it's going to be 0. Is my v value versus position, is it just going to start low and then kind of rise up and approach 0 as I head out to infinity? Is that what I'm going to see? And you say, well, the thing is, I got these 2 positive guys trying to raise the potential. If I'm way out here, what do I see out there? I see 2 positives and a negative. The distance from them, the distances will be, when I'm right here, the distance from the positives is a lot bigger than the distance to the negative. You know what I mean? But as I head out further, those distances start getting closer. You know what I mean? They're proportionally very, very similar. And so when I'm way out far, pretty much it's going to look almost like just a plus 1 q charge is kind of what it'll look like. I guess what I'm saying is, when I'm right next to this guy, my v value is going to be really low. But as I start heading out, these guys' effects, because there's 2 of them, right? Together, their potential might end up balancing out this guy's trying to lower the potential. These guys might raise the potential enough to balance it out because there's 2 of them. So there might be a point here where my potential goes from being negative near this guy, goes up and kind of crosses and becomes positive v value. And then as I head out to infinity again, it heads back to 0 again. Okay? So to test that, let's pick a hypothetical place to have a potential, we'll just say it's a distance x out, and we'll say, hey, when I add up the potentials, is there a spot where those will add to 0? So will my total potential 0 be equal to the V from, I feel like I should give these guys names. Do you want to give them names? Do you want to call them A, B, C? The V from A plus the V from B plus the V from C. Do you know what I'm saying? So if I did that, you say, what would be the V from this guy? Well, I'm going to use the formula KQ over R. So it would be K times Q. Now what's this R, this distance here? If I do that, I notice that it's a right triangle. This side is little a, this side is x. So the hypotenuse here, that distance would be the root of a squared plus x squared. Okay. I notice by symmetry, this is going to be the same, right? It's the same distance, yeah? Okay, it's the same charge. So I'm actually, this one and this one together, VA and VB and VC together, VA and VC together is just going to be double that. And then what's the V from B? So these two give me that. And the V from B, you say that's just going to be KQ over R. It's going to be K times negative Q over, and the distance away is X. Now, it's a negative charge. And when I'm doing energy calculations, I do include the sign of the Q. That's going to make this term negative. So that's it. So this is the equation for the total V value as a function of X. Now, is there a point where that total V will equal 0? Let's check it out and see if it'll work. First of all, if I made X equal to infinity, right? We know the potential is defined to be 0 there. Check it out. If this went to infinity, I'd be dividing by infinite. That gives me 0, right? Look at this one. As this shoots up to infinity, the denominator gets big, and this heads to 0. So my V value will go to 0 at infinity, or a negative infinity as well. Yeah? It should. It should. So we've got that. So, but now we want to see if there's another value, though. Is there another solution? So let's just solve this equation. So one thing I might do is I might divide all of my terms by K and Q. The K's and the Q's, every term's got a KQ in it, they drop out. Bam, 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 bam. All right? Let me move this 1 over x to the other side. So 1 over x equals 2 over the root of a squared plus x squared. All right? This is just going to kind of cross multiply here. Yeah? Okay. Now, I'm trying to solve for x, right? Is there a position x that solves this? So let's get rid of this radical, square both sides. A squared plus x squared equals 4x squared. I'm going to square that side, 2x times 2x. And so now just subtract the x squared over. That'll give me 3x squared. Divide through by the 3. I'll have a squared over 3 is x squared. Take a square root. And that's my answer, right? And my answer would be plus or minus that. So, yeah. So I'm going to get V to be 0 at a value like this, right? The root of a squared over q over 3. Okay. Or if you like, I mean, I guess you could factor that a squared out. So it'd be a times the root of 1 over 3, or a over root 3, plus or minus. Okay. And x is plus or minus infinity would also work. All right. So that's where the V is 0. All right. All right, cool. Okay, that was part A, right? Moving on. Can we squeeze part B in this part of the board? Sure. Part B. Now they're going to ask us about electric field strength. They say, if I have some position out here on the axis P, conveniently, I already sketched that, and they want to know the E field strength there. Right? So we want to know the E there at P. Okay. Well, we know that each of these 3 charges makes electric field around itself. And you say the field from charge A that's a positive, it would make a field going along that line like that. This is the E field from A. Charge C would make a field like this. And you say, hey, these are identical charges, identical distance. It's all symmetric. By symmetry, you should recognize that those vertical parts are going to balance out and sum to 0. The vertical components are the y components of field for those guys. This guy, this negative charge, he'll make a field towards him, so the E field from charge B goes that way. So I need to add the 3 fields to get the total field strength. So now, wait, how do I calculate that? We know that the E field from a point charge is KQ over R squared, right? And if I have multiple charges, I have to add them up to get the total field, right? But we got to be careful because E fields are vectors, and so they can partly cancel each other out like this. So that's what's going to happen here. These vertical components from these will cancel out. So I really just need to add the horizontal component of EA, the horizontal component of BC, and then the EB, right? And I see my total field is going to be in the x-axis, right? So looking at this then, my total E field is just going to be the x components of EA and EC. And these will be the same size, so I could just double the E from A, but just the x component, right? And then add the E field from B. I'm going to manually put the sign for direction on myself right now, okay? That E from C is going to go, E from B is going to go to the left. So EA in the x and EC in the x are the same size, so I just double one. Okay, now I just want the x component, okay? So how do I calculate that? So the way I'm going to calculate that, let's look at this guy. I have this angle theta there, right? This is the adjacent side, is the x part, the part we want. So you say, hey, that would be EA cosine theta. All right? So we're just going to have 2 times EA cosine theta. Sure. Okay, now how do I actually calculate the E field strengths? You say, well, I'm going to do that with this formula. So I'll have 2. Now EA, that's just going to be KQ over the distance. The charge of A is just Q. Now the distance, we figured that out before. This is square root of A squared plus X squared. That distance is being squared, so I'll just take the radical off. But then I need to multiply this by cosine theta. And you say, they didn't give me theta. So the trick to doing this, and I think you remember from seeing this from earlier, last unit, is this angle here, recognize that this is a vertical angle with this angle here. This is a triangle made up of E field. This is a triangle made up of distances, and we know these side lengths here, right? So I can find the cosine theta using this triangle. It's the same as the cosine theta for this triangle. So cosine theta is adjacent over hypotenuse, so it'd be x over the root of A squared plus X squared. That's what cosine theta is. So from a little trig, it's adjacent over hypotenuse. Sorry, that's A squared plus X squared. So I'm going to put that in here for cosine theta. Okay. All right, and that's a trick. Okay, I mean, we can't figure. We don't know the angle, but that's okay. We don't need the angle. We need cosine of the angle. We can figure cosine of the angle from this triangle. Okay, then minus EB, E field from B. That's just going to be KQ. I already made this negative myself for direction. We don't put a sign on the charge, right? In an E field or a electric force calculation, we put the sign for the direction of the field or force ourselves manually. We do the sum of the forces, or sum of the fields. And then the distance here is just x. This guy is just x distance away, right? And we're doing distance squared. Right, so that's it. So that's the setup. That's my answer, but that's messy. Okay, they're going to want us to tidy it up some, I would think. So we can tidy this up quite a bit. Let's say that total E field, right? Let's see. See, this is like an a squared plus x squared at the bottom, and that's an a squared plus x squared to the half power. So to the first, a squared plus x squared, to the first power times to the half power, that means to the 3 halves power. Okay. I notice that both of these terms have a kq in them. So maybe I've got 2 times x here, and then I've got minus. Maybe I factor out that kq. Multiply this whole thing by kq. Okay, I think that's as pretty as I'm going to get this. Yeah, I think that's as pretty as I'm going to get the answer. I mean, I could try to do something crazy and get a common denominator. No, this is it. This is it. Okay, so that was part B. Okay, takes me to part C. This third part says, using Gauss's law, determine the net electric flux through a spherical surface radius 2a centered at the origin. So they're saying, hey, let's make a Gaussian surface, a bubble, that's got a radius of 2a. See, here's a, 2a. So we're making a great big bubble centered on the origin, like this. And we want the total flux through that surface. Now, they're kind, and they tell you, oh, use Gauss's law for this, just as a reminder. And I go, okay, well, Gauss's law, you say, hey, that's, for electric fields, that's the integral over a closed surface of E dot dA, and that's equal to the charge inside over epsilon naught, right? That's our formula. And you're like, oh, man, this bubble, see how the charge isn't like it's not spherically symmetric. The charge is placed awkward here. I'm going to have a different field strength here than here than here. My field strength is going to be different everywhere on that surface. The field lines aren't necessarily going to be going perpendicular to the surface. The angles there's going to be changing stuff. This term, this would be a nightmare to calculate. You're like, oh, man. So wait a minute. What are we trying to calculate? The electric flux. Do you remember that that's what this is a formula for? This formula is adding up the total electric flux through that closed surface. We can't calculate this term, but that flux, we can calculate this one real easily. What's the total charge inside our bubble? Plus Q minus Q plus Q. That's just plus Q over a constant epsilon naught. That's it. The end. That's the flux. Ta-da! Okay, and that was part C of this free response problem. Okay, and you say, hey, that wasn't so bad. That wasn't so bad. All right. Again, the trickiness, I think, was when calculating the E field, because remembering it's a vector, that we got to take components, and in this case, this balance out, and remembering how to get this cosine theta when they didn't give us theta, right? We use this other length triangle to figure that out. This bit with potential, recognizing the fact that when I add up my potentials from the 3 charges, there may be a spot where, because there's 2 positives, their contribution to the V value might balance out the contribution of this negative charge. There's 1 negative charge at some point. Yeah, that's it. All right, so that's it for that one.